So guys, in this video we have come to the Reentrancy level, and I'm happy that I've solved all of these challenges, even though I've solved like most of them and they're not really that difficult. I mean, we learned a lot of stuff, but after we finish this Reentrancy, we'll go to elevator and these ones. And I think these ones are really harder, or at least for me different than the rest. So in this Reentrancy challenge, of course, we'll learn about the Reentrancy attack. And so it says the goal of this level is for you to steal all the funds from the contract. And things that might help, blah blah blah. So let's check out the code. We have an import. We're importing SafeMath, and because we use version less than 0.6.12. So the contract is Reentrance. And by the way, I'll just give it out now. I didn't solve the challenge because it has some problem to do with, I think, the version of the contract. Some people say it uses the 0.6 version, but has the syntax of like 0.8, so I don't know why, but I'll show you an example you can do that's different from this, and you'll understand this one too. This one is a simple reentrancy attack, and this type of attack is called single function reentrancy attack. This is a simpler version. And the DAO hack in 2016 was when reentrancy attack was first introduced to the world. And this reentrancy attack stole, I think, $50 million from the contract, and it caused the hard fork of Ethereum. That's why Ethereum exists as Ethereum Classic and the original Ethereum. So we're using SafeMath for uint. We have a mapping of edges to balance the edges that owns this much balance. We have a function donate. We need to call this to get some values into this contract on our edges. This will update our edges with some value. It will add the value we send, the ether amount we sent in this contract. We have a help or balance of function. This one says, just gives you the balance of U. Then we have a withdraw function. This is where the bug happens. So where is the error here? So we check if your balance is greater than the amount you want to withdraw, because you need to have the balance in this contract before you can withdraw it. Then we call this message.sender, and remember this can be both a contract and EOA account. So we send a transaction there with this amount. So we're sending the ether, your ether, withdrawing your ether to your account. This can be also a contract too. And to perform the attack, it needs to be a contract. First we make the call, external call, and then we update the state, make the effect. So this is where the hack occurs. So whenever you're writing Solidity, you should follow a design pattern called check effects interactions. So first you should check for something like with a require statement. Then you should make the effect, make a state change. So this state change should come like here first, and then you should make the interactions or external calls. But we're doing it the other way, the interaction and effects pattern. We're doing the effects later, and that's why if we make a call before we change the state, whenever we call this contract, we send their money, the contract's receive function will be called, and there can be a malicious code which re-enters this function withdraw. So that receive function can re-enter this function, and it can again recursively call itself and send some more tokens, some more ether. And we can see how attack works here. So we can have someone initiate withdrawal. Of course, first he has to send some money into the contract. Then the withdraw function performs this ether transfer. And this ether transfer, if it's to a contract, the contract has a fallback or receive function. And this can be overwritten by the developer of the contract. And this fallback can again re-enter and call the withdraw balance. And the state change, you can see it's not done yet. And because it's not done, when we check the state, it still says that this person has some ether. So it will send ether that's basically from other users to him. And it will do this over and over and over again until it drains out the entire contract. And that's all because the state change didn't happen before the interaction. And that's even a simple example, a single function reentrancy attack. But nowadays we have more complex cross-chain reentrancy attacks that send some very valuable resources you need to check out to learn more about them. So what is this cross-chain function stuff reentrancy? So we have a transfer function and a withdraw. And again, this withdraw can call a contract with a malicious fallback overwritten function. And when it does this, instead of re-entering here into the withdraw function again, it can call this transfer function. And this transfer, checks if you have some balance, and it sends that balance to the attacker's contract. And it will pass this check because the state was not updated here in the first place. So again, the attack, I guess, it's kind of similar because again it relies on you being, how do I say, a crap developer and not learning about how to do design patterns properly in Solidity and put your state changes before the interactions. But now instead of re-entering, it calls this transfer function, which will transfer the balance to some address because it doesn't, it says the balance is still 0. I mean, the balance hasn't been subtracted yet. It's not set to 0. And how can we solve this reentrancy problem? Well, first I think you have this example from Eat the Blocks, where the way he solves this, so the victim account is this savings account. And why is this possible? I think because we haven't checked for with a modifier. There is this non-reentered modifier from the reentrancy guard contract from openzeppelin you can use. This is called a mutex, and this basically prevents this function from being re-entered. Also, this is my code that I've tried to solve this challenge and it didn't work. But you can, I guess, always try this on a testnet, see if it works. And that's pretty much it for this video. So thanks for watching.